What's here? Well, it's a Wednesday. They show up on Friday. I noticed. I should change the schedule. Hope someone's here. Okay. Okay. What's I need to do? I gotta open this thing. Gotta open this thing. Yeah, I'm really not functional today. I shouldn't have driven a car, you know. That's what worries me. I'm like driving a car and I haven't slept, and it's like, you know, kind of for no reason. All right, so we got that, and then I want to open. I'm going to open up this guy too. Get the new house. That's good. Okay, that's good. So yeah, I might as well go to this is part of it, right? I guess this thing, right? So anyway, so let's see. So this homework, yeah, it was a kind of a bloodbath. I think that the low was 66 and the high was like 88 or something like that, 84. So it wasn't a good homework. So I want to go through it a little bit. To go through it, you just need the paper. And this rouse thing, right? So the questions in here, let's see. Figure 311, this is the other paper. So let's see. Widener. So he shows, yeah, people didn't really get much out of this. So he shows these two, the black line and the points. And this is what, let's see. This is either the viscosity. So if you're doing a time, so you put a Couette viscometer, a cup and bob, and you just spin it, and you have the torque and the speed. So then from relationship to those, you get the viscosity. That's the viscosity. That's this eta thing. And then he also measures it with like a cone and plate and oscillatory low amplitude. And then he gets the storage viscosity from that. So that's the N prime, eta prime. So, and they're right on top of each other, which means the frequency and the time are the same, right? In other words, you can the two measurements. So that's good. That means that you can substitute time and frequency. So, like if you look, like one thing in this paper, he's using like DWS, right? Which is, so wherever that equation is, it's like this equation. So you'll notice like this thing is time, right? It's like frequency. So he's measuring a time measurement and he's converting it to frequency. So it's like basically he's using the Cox-Mertz rule to do that. Like that's assuming that you can do it, right? So there isn't, the rule means that it isn't proven that you can do that. Like it's not a fact of nature, it's just like a rule, right? So anyway, so he's using that rule to do that transform. So that's kind of one major thing he does. And then I guess people mention, I don't know, the answers weren't that bad. It's just that people missed that point. And then they also missed that he's doing the two measurements here. Like he does the steady shear measurement, which is in like this figure, where he gets the specific viscosity versus concentration. And then he measurements G prime, G double prime. He does that with a normal frequency, low amplitude, small amplitude oscillatory strain. So SAOS. There's an E in it too. Anyway, with the cone and plate, and then the other way he does it was DWS, which uses the Cox-Mertz to get the answer. So that's kind of that thing. Then his equation 4. So I went through this in class, equation 4, whatever it is.
Yeah.
Where did I go by it?
Yeah.
Oh, here. All right, this thing. So let me just do it again. Right, so let me write down what the equation is first. The equation is number 4. He's got the tau. It's got so that's what he has, and he doesn't say where he gets it, but basically, so you need to use the oh. Oh yeah, there it goes. Right. Right. This is just Brownian motion. Remember, like time, square root of time, that thing. So anyway, if you say that if you're at the relaxation time tau, then the distance that you travel is like one blob size. So one blob moves one blob size. So this distance that you traveled is a blob size squared. And then T is tau, and then you have the diffusion coefficient. And then if you use Einstein-Stokes for diffusion coefficient, it's KT over 6 pi times the solid viscosity times the size, which in this case is that size, right? So that's how you get this cubed to the size. That goes over here, you get cubed to the size, viscosity, to get that, and the KT, right? And you have that's equal to tau. So that just works out. And then you just plug in the expression for that in terms of concentration, which we got the thing, but the 3/4 to the n power. But if you go through that concentration blob thing, you have like that the blob size is this thing, and nu is 1 by df. Right. So this thing just comes from the definition of the blob size. Just plug that in and get that other part to it. So that's it. That's all there is.
I think it's a particular equation. We will start from the Brownian motion.
Need Brownian motion.
Okay.
Yeah. To get it. I mean, I didn't know that offhand. I just tried everything, and there's only so much in your toolkit. You only have like 2 or 3 equations, and that's one of them. Turns out like that one works. So that's how I originally did it. But if you think about it, it kind of makes sense too. You want to think about it, but you don't. Basically, there's only so many equations. There's like R goes with NL squared, R squared, NL squared, this equation, the Stokes-Einstein equation for diffusion. Like we only have like 3 equations we're using over and over and over again. Right. And then this exponential minus T over tau thing. We're using the same equations over. I hope you can see that, like, so this is a case where you need the same equation. Right. So when in doubt, just use the diffusion Brownian motion equation, I guess is the theme. Figure 3. All right, so this one, it says the inset, right? And the other one's inset too. So figure 2, figure 3. So the inset here is based, this is a position of the crossover, right? So at low frequency, it's flow, right? So the storage modulus has power 2 in frequency, and the loss is power 1. Oops, sorry. All right, so yeah, a low frequency, it's flow. So you have power 2 for the storage, power 1 for the loss. And that means it's a liquid. The loss is bigger than the storage, so it's a liquid. So everyone's happy. And then over here, this should plateau out, but it doesn't. That's why it's not Maxwell, like it never plateaus out, right? To be a Maxwell, it has to plateau,
Okay.
right? It doesn't plateau, it just keeps going up. So anyway, but there is a crossover point, and that's where it becomes solid. So that's called that 1 over that frequency is the viscoelastic relaxation time. That's the time it takes for the solid to relax. Once it's relaxed, it's a liquid. So it's got something that makes it a solid. That thing has a time constant associated with it. So it's a temporal solid. So if you give it enough time, it'll be a liquid. But if you give it less time, it's a solid. That's the viscoelastic relaxation time where the two cross. And on this side, the solid's bigger than the liquid. It means it's solid. So it's solid rubber here. And then it's a liquid, viscoelastic liquid over here. Right. So anyway, so that makes sense. If you all right, so as you dilute it down, the entanglements get more dilute, right? So you have, in other words, the chains are more separate, and as you can get to a point where there's no entanglement, CE. And if you go just above that, then the entanglements are sparse. As you get higher and higher, the entanglements get denser and denser. And then this relaxation time changes with the concentration. So this viscoelastic relaxation times are related to the concentration. If you can, so if you have two systems and one's at one concentration, one's at the other, and you want to make them have the same dynamic response, and it's a simple relaxer, so it only has one relaxation time. It's like a Debye relaxer. It's just got the exponential minus t over tau. Then you want to have that one time to be the same. So that's how you get the things to match up. You match up with that time, and then that works somehow. If it didn't work, then you wouldn't give that argument. Basically, you say, like, you propose this would be an argument, like how you could shift these things. First, you'll look at it and say, oh, they all cross. What happens if I put them all in the same point? And when you do that, they fall on top of each other. Right. So there's various ways to get at that. Once you get it, then you can make up this story about viscoelastic relaxation time and how that would be the point that you would match. Right. But that could just as easily not work. See, I mean, keep in mind that these things are just stories people make up, right? But anyway, it works great, actually. So then the other part of this, that's part one of this thing. What is the crust? So some people got that pretty good. Some people didn't get that at all. And then why is it a useful point? And then what's the equivalent point for time temperature superposition? So you're going to do something like that. So you're going to have a shift factor to shift the curves around, but you're not, first off, there's no shift in G. Even though people make up a shift in G when they do time temperature superposition, there's no explanation for why you do a G shift. In other words, you can do a time shift because it's time temperature. So you find a factor that relates time and temperature, which is an Arrhenius factor. So you're going to go like, so you're going to have like exponential minus energy over KT. So you're like your viscosity or something, right? So you're going to have, and then this over that, or ln of that over that is ln of AT, the shift factor that's going to relate time. So viscosity is kind of proportional to time, or like 1 over frequency, right? So. And then, so this AT can relate different frequencies at different temperature. That's minus E over KT. Or if you want to have a Vogel temperature, it's T minus some base temperature that isn't absolute zero. Then energy becomes enthalpy minus TS. Right. So then that will give you the WLF if you move it around enough. Right. So. Anyway, so that's the time temperature superposition idea. It's based, this is Arrhenius, and then this is a modification to Arrhenius, 2 modifications. Instead of energy, enthalpy, and entropy, instead of just temperature, you set a base temperature. It's not absolute zero because the stuff turns into a glass at some temperature. So motion stops there. If you're talking about motion over here, then you have to have some other base temperature. All right, so it's nothing like this common viscoelastic relaxation time in this thing. Not exactly. I mean, and also you're only shifting frequency here. You're not shifting the G part at all. So But people, yeah, people do shift the G part, and you have to shift the G part to make it work. So that's just like pull it out of your hat and do it, you know, so anyway, you end up with this kind of the same thing, but the argument's quite a bit different, and you aren't basing it on a point here. You're basing it on just that the Arrhenius function works. It's based on a function. It's not based on a point. This is based on a point. The other is based on a function. It's interesting to kind of compare the two. This one is like not commonly used, this concentration shift, right? So this is just something that they kind of came up with, I guess, in the 1990s, or some of there's references to it here. Or whenever this Wagner is one of the early ones. That was 2000 something, I guess, 2006, I think. Let me drag this up. Yeah, 2006. So this is something kind of within the last 20 years, this shift of the concentration, but it works great. I mean, this is like amazingly good. Anyway, so it's that business. Then figure 5 shows Maxwell-like behavior. Explain why it's like, so it's like and not Maxwell because it doesn't reach a plateau. That's one thing. And then, but if you're talking about Maxwell, you're going to have to do these, like, first of all, like in this, all right, so Maxwell, everyone said, oh, like, and you didn't draw it. Like, if you're going to say spring and dash pot, you have to draw this. Okay. You have to draw that if you want to say that, but I don't think you should even mention that. You know, what you should say is, well, I'm looking for log G prime, log G double prime, and I want them to behave like this versus log frequency. And then I want this guy to be like that. Right. So that's the by single relaxation. That's exponential minus t over tau. Maxwell simple relaxer, single relaxation time. Like you just have one tau. Right? You could have a sum of these that would give rise to a spectrum, right? That if you have a sum of those, give rise to a spectrum, you say H of tau, like the relaxation spectrum. Right. So anyway, so you had to show these two plots, and then those two plots were related to the to that equation that you have that I thought I wrote down here, so I did it right. But yeah, so this equation. So you have G star is 1 over J star equals viscosity, zero shear viscosity, frequency, zero shear viscosity, frequency, recoverable compliance plus I. So the J star is J E0 plus I over like that. Okay, so this is flow, and this is when you first pull. So when you first pull your gum, so you're going to put a weight on gum, you have to pull it. So immediately you let the weight go, and immediately instantaneously pulls down, like, and that would be recoverable. That's just like a Hookean elastic. So it would be recoverable. Like if you took the weight off, it would go back up. So that's what this J naught is. And then the gum will slowly stretch out. But if you take the weight off, even at the end, it'll still come back. Right. So this is called the recoverable shear compliance, JE naught. This is the plateau viscosity. Like if you plot viscosity versus shear rate, and then it plateaus, Newtonian viscosity, and then it has a power law decay, log. Right. So that's a zero. So those two numbers. So with two numbers, you can predict any of the properties. That's the idea. You have and it's easier to talk about it in terms of compliance. One thing always began with dielectrics, and compliance is the only way you do dielectrics. And for another thing, it's simpler to think about it in terms of compliance, even though the measurement's done mechanically with a shear modulus. Right. So because you can, because you don't want to have a constant force and watch it stretch forever. But you have some limit to how far the gum can stretch. It reaches the table, you're over. Right. So, but as far as the putting a fixed strain on it,
that's simple to do. So if you're just saying, I'm gonna let the gum go only that far, but the strain is gonna oscillate, then that you can do mechanically. You can set that up in an experiment. So G is like the thing you want to look at, but J is the thing you want to think about, I guess is what it comes down to. Anyway, this equation predicts those curves because if you remove that by multiplying by the complex conjugate N0, J0, whatever, you'll end up with the plateau, the Newtonian viscosity times the compliance, the recoverable compliance, and then the minus I times the plateau Newtonian viscosity frequency divided by this thing. That thing's not squared here, JE0 plus 1. Then you end up with that equation. So you have, this is the storage, or this, yeah, this is G prime, this is G double prime. It's got the minus I here. So what does this thing do? Well, here, I got that here. So we already kind of went through that, but it's maybe a little bit less messy here. That's why I brought this up. So once you have that thing, so this is just 1 over that, this is that. So it's got the immediate compliance, recoverable compliance, and the flow part. And then 1 over that is this, and then that's can be rearranged to be this, the storage and the loss. Right. And then if you say, well, what happens in the flow region? So in the flow region, the frequency is low, so that term squared is small compared to 1, so that goes away, and you just have this square of frequency. So that the storage part goes with the square of the frequency in the flow part. And the loss part goes with frequency. That's why you get a crossover, because this is going faster than that. And then they cross at the viscoelastic relaxation time. That's related to this JE0 and zero shear viscosity. The ratio of those two gives the time, the viscoelastic relaxation time, which is the crossover time. Then that's it, I guess. So basically this equation, oh no, that's not it. That equation, where is that? Will give you those curves, right? In other words, if you plot this function, it's the same function for compliance and for modulus if you change what the constants mean. But so anyway, if you divide by omega tau and then take a 10 to the log of it, then you see on a log scale, this one will go to 0 below 1. I mean, this thing will get large below 1, that thing gets large above 1. So 1 over it gets small to get the peak thing from that. And then this thing shows that kind of decay. If it's the modulus, it's kind of 1 over this, so it goes up instead of down. Right. So anyway, so basically that's the Maxwell signature. You need to draw that plot, you need to show those equations. And then if you look back at the paper, anyway, so that was kind of missing from everybody. So if you look at the paper, yeah, he's kind of showing that. I mean, it doesn't reach a plateau. That's the main thing. So the modulus doesn't reach a plateau. And this thing, the loss doesn't exactly show a peak either. So it's Maxwell-like. It's not purely Maxwell, because it's got multiple relaxation times and it's got a spectrum. It's not a single number. Right? So anyway, so that's kind of where that's going. You can see that you could mess that up. I mean, and then this thing. So he says right in the paper, this figure 6, I say the inset of figure 6. So this thing. So what is this thing? What is that thing? It's the shift factor versus concentration for this displacement. And these numbers, I mean, he says, and the reason I ask is because he says it here. It should have been pretty easy, I guess. I mean, apparently it wasn't, but no one got this. I mean, 5 and 8. So in the beginning, he goes through a whole chapter on like where all these scaling laws come from, and equations 5 and 8 predict that y and z should be the same number and they should be 2.3, and he gets 2.5 and 2.6 from this thing. And when that happens, that's Rouse. So that happens, that's Rouse. I mean, people had stories about the concentration of things here, but I mean, basically, I was looking at the inset and just what does this mean? So you read that, but no one did. It's probably insignificant. And then 9, I was looking for 9, one group did okay on, but this is the crux of the whole paper. Like he says that this shows that he can observe the Zim to the Rouse to Zim transition. So understanding that plot could be important depending on if you're interested in what he's talking about, which you might not be, but anyway. So what's going on? So you have the viscosity and the frequency, right? So if you have so we should have that in the plateau that we have like G prime reaches the plateau, which is called G naught, right? The plateau, and that should be 1 over in entanglement times L squared, like KT. We should be able to get the number of the crosslink density from that plateau, the entanglement density from that plateau. All right, so if you look at it, G times strain gives you stress, right? So, and stress also equals viscosity. So, or I mean, in another world, like a different kind of stress. So the units of stress and stress are the same, and this guy has units of frequency. So G naught has to equal something like viscosity times frequency has to have to do with modulus. I mean, if you plot viscosity and you have a constant modulus, then you should get this to the -1, and that would be this plateau part. That's the signature of the plateau. If you plot the viscosity versus frequency, then you should get this -1 thing, right? So he kind of sees that. He gets -0.77. So that's his entangled part. So, right, so that's a starting point of this plot, right? So you're looking for -1. He says what you look for. Look for 0.5, 1/3, and 1. -1. -1 is just this entangled plateau. You have a constant modulus. The viscosity has to go with frequency to the -1. That means you're at the entanglement part. And we know it's not going to be perfect -1 because it didn't reach a plateau in the other curve. If it had reached a perfect plateau, then this would be -1, right? I mean, it could be. Anyway, so that's one point. So then you got to think about the bells. So if you have a bell that's got a low frequency, that's a big bell. And if you have a bell that's got a high frequency, that's a small bell, right? So structurally, when you look at this plot, you're looking big distances and small distances as you go across it. People talk about the concentration, which is another way to look at it, but that's not, when I said structurally, the concentration isn't exactly it. Anyway, it turns out like this size thing matches up with the concentration thing. If you think about that, when you go to dilute, you get to bigger distances too. Like, so anyway, so he's got, so as you're going across, you have this mesh, entangled mesh, which should be -1. And then you get to the point where you can see within the mesh and the chains can like weasel through the thing. So you get to this Rouse motion part. So they're confined, like if they want to move sideways, they're stuck. But if they want to move in a straight line, they're fine. And that's where this -5 part comes from. That's Rouse, right? So you're thinking about frequency as size and trying to imagine a cartoon of like, you're zooming in. Who's the lady with the school bus? The thing with the little kids. And she shrinks her bus down into your human body size and goes through your blood vessels. I forget her name, but my kids used to watch that. I probably watched it, but anyway, so that's, you're shrinking down as you go up in frequency to smaller sizes. Your school bus is getting to be the size of the network, and you're traveling through the tunnel, and then you're shrinking even more, and the tunnel disappears. You're just floating around. You're just a Zim coil floating around, right? So as you're going across frequency, you're going from, oh, it's a rubber, it's got a single modulus. And then you go to higher frequency, and then, oh, I'm moving in a tube and I'm driving my bus around. In my mind, I'm thinking about the bus. I don't know why, because they do that. They shrink into the human body, and then they see the red blood cells. And finally, they see the virus and kill it. But So anyway, and then finally you're just free coils, and you can't see the walls of the tube anymore. And that's when you're in the Zim thing, a nice 1/3. So he claims that this proves that. And it kind of does, I guess. I mean, the thing is, usually when you talk about a power law, you want to have at least 1 decade in whatever the x-axis is, and it's not clear that there's defined power laws here. Exactly right. If you want to believe it, like I could say oh, my magic number is minus 0.4. Well, there it is, minus 0.4. Anything could be in that. So see, it isn't, the minus 0.77 is kind of clear, but it's not the right number. And then these aren't clear at all. And then so anyway, and then people talked about concentration on it. So that's another angle to this. The high frequency is the lowest concentration, which corresponds to the smallest size, which corresponds to the Zim behavior. So when you go to low concentration, they can move around easier, so you get Zim behavior. So they act like just coils. You go up in concentration, and the entanglements start to affect it, and you get to kind of what ends up being larger size here. So the concentration and the size are kind of related to each other. But the connection between frequency and size isn't really that clear cut. Okay, and if you look at it, this isn't like 10 times bigger, right? Each decade on the frequency scale isn't 10 times bigger in size. In fact, it's a lot more. So like when you get to the left-hand side of the scale, you're really talking about meters, like some huge length scale. And when you get over here, you're talking about angstroms, right? So this scale, it's like 1, 2, 3, 4, 5, 6, 7, 8 orders is really like 20 orders, something like 10, 15 orders in terms of size, right? So there isn't even a 1-to-1 to decades on this between size. So the rheology can actually measure a huge range of size, an incredible range of size when you think about it. But there isn't really a direct connection between rheology and structure, because anything we'll see in the next paper, which is going to be along these same lines, and that it's complicated. You'll see that the nuances to rheology is that it can become like a huge mess. So it's basically, in general, like you want to understand it, and everyone's grasping to understand it in terms of a structure. In fact, that's kind of a lie. You can't get structure from rheology. All you can get is a response to it. It's a constitutive parameter. You don't know what it's really describing, right? So it's a little bit of a twist to it. Anyway, that's the whole thing. So I thought I'd go through it because everyone did kind of bet on it. That's what I mean by structural perspective. It means you're going to say frequency and change it into size, and just make up some kind of cartoon about what's going on. And then you can feel warm and fuzzy about it, but then you have to remember that that's probably a lie, right? So, I mean, it's good to feel warm and fuzzy about it, but anyway, so this is that business. So let's see. Any questions on that stuff or anything? Oops. All right, so let's see. So we did this. We went through the Zim thing. We mentioned the results of the Rouse. Then I went through the Rouse, and you end up with this equation that relates the inverse of the relaxation time to the sine squared of this phase factor. And then if you use a constraint like cyclic, find out the phase factor goes with 1 over molecular weight, it's squared, so that the tau goes with the molecular weight squared, which is the thing, that's the prediction of the Rouse. Relaxation time follows and squared. For the Zim, it's 1 over df, so end of the 1 by df. So there's quite a bit of difference between Zim and Rouse in terms of that. So that's one part of this. So, and then it doesn't matter what what boundary you need a boundary condition because you have 4 unknowns and you have 2 equations. So you propose a solution, you have that equation, you have 4 unknowns. You can relate 2 of the unknowns to each other by eliminating 2 parameters of 2 equations. Then you need, in order to solve that equation, you need another constraint, which is going to be cyclic or free end boundary conditions. They give kind of the same answer, right? So anyway, and then I mean, you can take just from a guitar string analogy that the main tone you hear is the tone, the first order mode, like the E tone of the string. Say, and you can calculate where the energy distribution is and find out it's 1 over the mode squared. So basically, the energy of this, if the mode is 1, is going to be 4 times bigger than mode 2, etc. Right? So basically, the lowest order modes are the only ones that matter, and in that case, you can talk about the Rouse as if it's a dumbbell with a single relaxation time, as Rouse relaxation time. Then there's this business that we saw, I think, in that paper, and you'll see in this paper this week that you have. So we have the network, and you get to sizes smaller than network, and then you have this transport through the tubes, and that's following Rouse behavior, and the signature of that is this frequency to the 1/2. So like, where does that come from? So down here we have G prime goes as frequency squared, then we reach the plateau, and then it's going to go to this Rouse behavior out here at high frequency, where we're inside the tube. Again, like small size, big size is kind of the idea here. Let's see. Huxmertz we had there, Kramer's chronic we talked about. I think I mentioned it. And then the Maxwell model we've done. And then I talked about the Cole plot. So this week there's a Cole plot too. So, and basically the signature of one, you have a single exponential relaxation, like 1 tau. Cole plot gives 1 circle. If you have multiple taus, you get multiple circles superimposed. So the data will have like 1 hump and another hump and another hump. If you have 3 relaxation times that are discrete from each other. So that's one way to look at this kind of dynamic data. All right, and then terminal region. We did this already. The low frequency. So if you get to low frequency, then this number squared gets smaller than 1. Then you can just talk about the top, which is a squared frequency, and the linear frequency. And then all right, so the Rouse thing. So where does this square root of frequency come from? Right. So we had relaxation time goes with this molecular weight divided by the mode. So if mode is 1, it's the molecular weight squared. Right. And so this relaxation time, if you think about it, like if you have a relaxation time 2, it's 4 times smaller relaxation time. Means that if your time is tau p or tau Rouse, and you want to know what is a second order mode doing, well, its relaxation time is much smaller. So you're giving it like 4 times the time it needs to relax. So everything of higher order mode is gone. It's totally relaxed. And all you have are the mode where you are and the modes below, the lower modes. If you're at mode 4, so the guitar strings into 4 loops, and your time is, so you can excite the different modes on a guitar string. Like if you sing, or if you have a glass and you sing, you can reach the frequency of the glass and blow it apart, right? Same with a guitar string. If you sing one of the modes, you can excite the 4th order mode. The guitar will sing back the same frequency. It's a resonant frequency, right? So basically, all right. So this is kind of how this thing works too. So you're going to have these relaxation modes where the thing can vibrate at the different frequencies, having different tones basically. And then the ones at higher order modes are totally relaxed, so they don't give any sound. So the higher pitch ones are not going to respond if you excite it at that pitch, right? But the lower pitch ones will respond, right? So anyway, that means that the kind of the energy stored. So the modulus is like the energy that's stored. It's like the KT energy per vibration or per monomer that's vibrating is a modulus. Okay, so like the modulus is coming from the vibrations in this case. So you want to figure out like how many vibrations you have at a given frequency or a given time or given tau, right? So that can be worked out. So that's the origin of this square root term, the frequency of the 1/2. So how that works is you have to use this equation that the time goes with, so square root of time goes with n, right? So you have there are p unrelaxed modes, each of segments composed of segments with kT energy per segment, and each segment, so how many segments are there for a given mode? This number, total molecular weight divided by the mode number. So if you have the guitar string split into two, each of the modes has 1/2 of the molecular weight of the guitar string in it, right? So it's going to have more energy, kT times each of the whatever components of the guitar string are, right? So anyway, and it's going to have volume b cubed. So if your volume fraction, so if you want to know number per volume, it's the number density of these vibrating kT things, which are the monomers, each of volume B3, then you're going to have the volume fraction of the polymer that's in the system divided by the volume of each of the monomers, which is going to be the volume of one monomer, B cubed, times the number of monomers will give you the number per volume of the, you want number per volume times kT to get the modulus. So the modulus is the number per volume of the vibrating things times kT energy for each gives you this, right? So, and P is related to, so from this equation, P, so you have P in this equation, the mode, that's going to be the number times the square root of the time. So you can plug that in to get the modulus. You find out you'll end up, the square root of the time shows up in that. G, the modulus goes with the square root of time, 1 over the square root of time, right? So basically, that means the modulus goes with the square root of frequency. In other words, 1 over time is frequency. So 1 over square root of time is square root of frequency. So basically, just by some kind of algebraic manipulation of this, you can get the storage modulus as the square root of the frequency, which is what you need to talk about this thing. G prime goes with the square root of the frequency for the Rouse. And then, so that's kind of just where that comes from. If you, all right, so you can take that, and then you can take that expression for G prime and then plug in our exponential. So that's like the prefactor at your time. And if you want to know, put in your relaxation time thing to get the G as a function of time, and then you can integrate that. Then you can get these kind of complicated Rouse expressions. So the advantage of these is that they can be verified by experiment where you have just pure Rouse behavior. So you have these things are going to give you, if the frequency is low, then 1's bigger than omega tau r squared. So this thing becomes 1, and this thing becomes 1, and that thing becomes 1. So this whole term becomes like a constant, and you just have G prime goes with frequency squared, and that's the prefactor. So that's the normal flow when you see that. And the other expression gives you just frequency. Same thing, this goes to 1. You just have the frequency, and that's prefactor. Right, so this Rouse expression works for fluid flow, and it also works at the high end. You'll get that square root dependence, this thing, and you find out that for Rouse, both the storage and the loss follow the square root dependence. All right, so that's kind of weird. Like usually we're expecting that loss and storage to have different behaviors. Like with the signaled by relaxer, the loss has a peak and the storage is just a flat number when it gets to high frequency. This thing is a square root, and both follow square root. That's kind of odd. So in the 90s, this guy Winter, I guess 86, but later on, so he made this kind of into an industry, I guess. But and also this new guy, Yevitt, right, worked for Winter for his PhD at UMass. Henning Winter's a rheologist there. Anyway, he's pretty famous. He's famous for this idea that when you get this kind of behavior where the loss and storage both follow the same power law and frequency, that's a gel. That's the definition of a network, basically. And there's a lot of math involved. Basically, when the loss and storage, log of the loss, log of the storage follow the same dependence and frequency, that means you have a network, right? So this idea in the Rouse, that you have G prime and G double prime are both proportional to the frequency to the 1/2. So you have a power law dependence, and they're the same for the two, tells you that the thing's a certain kind of network. That this Rouse motion is reflecting like basically a network behavior. Thing acts like a network. And you can see that can be verified. Like you can verify that works. In other words, storage goes power 2, loss goes power 1, and then they match up and they have a power 1/2 at high frequency of this poly 2 vinyl pyridine. Hodgson and Amos. Eric Amos was, he's a Polymer guy from the 90s, I guess. I'm not sure what he's doing now. But he was at Southern California, USC. Then he went and became head of NIST Polymers. Then he went and became head of Akron Polymers. So he's kind of like became a bureaucrat, but he did a lot of solution viscosity stuff and dynamic light scattering. Anyway, so this was that business. Then what else is in here? This just shows that idea that if you can take the recoverable shear compliance and then the plateau viscosity or the Newtonian viscosity gives you this relaxation time. If you integrate the storage modulus as a function of time times time, you get this relaxation time. So it's different, and basically that's the crossover, 1 over the crossover frequency. So anyway, so that's kind of the behavior we're looking at. This is viscous flow, that's the plateau, it's the entanglements, and then we get to Rouse behavior, we get to small size, and then other things happen at the high end that we kind of talked about. So let's see. This I want to talk about, just to mention. Okay, so people do. So when you extrude a polymer, right? So it has this normal stress thing that happens. So let's see. So you'll see people. There's papers on this too. So it's an interesting thing, right? So you extrude through a die, and then then you get a die swell, right? So it's going to go out like that. So you have the viscosity goes with the shear rate, some power, some negative power, like -2, I guess 2.x, right? And then this thing can also be related to shear rate. So you talked about the force, it's how like the normal force here, so tau 2.2 or tau 3.3, and that's going to be this normal stress coefficient 2.2 times the shear rate, basically the shear rate squared on this thing. Let's see, viscosity and shear rate. All right, so this thing would be tau 1.2 is the viscosity times gamma dot 1.2. That's just the definition of viscosity. And then the viscosity is going to be a power law. You plot log viscosity, log shear rate. It's got a Newtonian part, and it has a power law decay of something like 2.x. So, and then this thing also. So you have this first normal stress coefficient. Right, this gamma 2.1, and then that also can follow the same kind of power law behavior. Right, so it's going to be kind of the same thing. So you can see, so like this is plotted for polyethylene, 150 degrees C. That's the Newtonian viscosity, the plateau, and then there's a power law decay. Right, and the slope is So if you have 2 decades by 1, that's -2. I guess it's minus. That would be -2.
So the bar,
It's like a half, right? Yeah.
the bar,
For this part, yeah, I think it's a half. I guess my 2 should be a half. So the viscosity is going as -1/2 here, right? And then this, you can see where this is plateaued, that is also plateaued. And then it has a steeper decay, a steeper dependence. Right. And then the other thing plotted here is the recoverable strain. So if you shear it and then you stop and then watch it kind of spring back. So say you continuously sheared it instead of oscillatory, and then you just stop and then let it come back. That would be the recoverable compliance, and the recoverable strain is basically that compliance divided by the stress. Now, stress is compliance times strain. So that strain is the stress divided by the compliance. So it's this is 1 over the recoverable J naught, the recoverable compliance. So that's the inverse of the recoverable compliance. But anyway, so this thing, anyway, I just wanted to mention this. I guess see, it's going to be dependent on the strain rate squared. This is dependent on the strain rate. So this shear stress is strain times viscosity. This first normal stress difference is the strain rate squared, right? And then this thing also, both the viscosity and these 2 normal stress coefficients have power law dependence in viscosity and strain rate. So, but they'll have a Newtonian plateau where everything's relaxing. And there's this tail over where there's a basically a relaxation time for the coils under flow, which is different than the viscoelastic relaxation time. And that tailover point happens at a different point in frequency than our viscoelastic relaxation time, but they're related to each other, but they're not the same number. Anyway, so people study this a lot now, this kind of normal stress development, because it's important to, for one thing, like the 2 numbers are different numbers. See, you're shooting out in the X direction, the Y normal stress is different than the X normal stress. So it can make like so that if you spin in a fiber, it's not going to be circular, it's going to be like an ellipsoid cross-section, ellipse cross-section, right? So, and so basically, and I showed you that early on, like if you have a teardrop bubble rising, it'll have a tail because this normal stress is squishing it. But if you look at it 90 degrees, it'll be like have fins on it. And the other way, it'll be just a teardrop shape. So anyway, so why those things happen, I mean, people make up stories about it, but basically nobody knows kind of constitutive parameters. So it's that business. And then we got 5 minutes. I just wanted to talk briefly about the reptation thing, right? So maybe just say, so the chain in a tube, and then you can find the chain and you do Rouse motion in 1D. That's the idea. So it's still based on the Rouse model, but it's in 1D. You say that the pathway it takes is Gaussian, right? So then you can talk about you have a kind of a Brownian pathway, and it's going in a straight line along the tube, but the tube is bent, right? And that bending of the tube will give you this extra power kind of, right? So in other words, the relaxation time per Rouse was n squared. This is the same, and that's because of the n by p is time thing from the sine squared and the solution to the differential equation. So, and you plug that into this tube that's a random walk, you end up with n cubed. That's the bottom line. So basically the reptation time is going to be n cubed, and then the diffusion coefficient is going to be n to the -2, or you had n to the -1 per Rouse. And that translates into that if you plot this, you would predict that the viscosity will have power 3. It actually goes to 3.4 consistently across everything in the world, right? So I mean, probably the difference between 3 and 3.4, that's a log scale, so it's a big difference, right? But basically, I mean, you could ignore it, but they haven't. So basically, the 3.4 has been explained by a number of different people, different ways, you know. I mean, one way is that you can talk about that the tube itself has a relaxation time. So the chain has a relaxation time to transport through the tube, but the tube itself is also changing with time because it's made up of other tubes. So the tube is made up of other chains, all of them are relaxing at the same time. You can imagine that would become complicated, right? So somehow you can get 3 point something. I mean, no one exactly gets 3.4. Basically, you can get 3 point something from that. So there's a lot, I mean, there's a lot of simulations, a lot of theory going into reptation. I think that understand seems like the papers mostly talk about Rouse, actually. It's like I Googled and you can find a lot of papers that mention the word reptation, but that's all they really do. In other words, you can find 100 papers that are published last month. If you search reptation papers last month, there's 100 of them. But if you go into any one of those papers and then you search for reptation, you'll find out it was used once in that whole paper. And all they did was say like, oh, that's because of reptation. They don't actually use the concept, you know. And the papers that are using the concept are like really complicated simulation papers or really complicated like theory papers that are kind of almost useless, you know. So reptation's like a cartoon idea to explain like what's going on here, but generally like people aren't exactly. Anyway, you'll see this week they kind of talk reptation, but they're really just talking about Rouse behavior for the paper this week. Anyway, so that seemed to be what this current status is in this stuff. So I'm not going to really talk about reptation, just to say that there's that prediction. It's in that book by Colby and Rubenstein. Like that book goes through pretty in this fairly simple way, reptation, if you want to read about it. But anyway, so anyway, Monday I'm not going to be here. So you got to go to the ACS meeting. So I was going to like record a class, I guess. And the topic I think is going to probably be like nano composites or something. Because I looked, I want to do membranes, you know, but basically probably better to put it off a little bit and do like live lecture on it a little bit. Anyway, membranes, it seems like there's not a lot of physics in it, but anyway, we can cover it. But basically, it's a lot of topical application things, so it might be good to look at that. Yeah, versus artificial intelligence and stuff. I think that's a little bit far from us right now. I have the slides on the web page for artificial intelligence, but I mean, we wanted to do membranes, right? So we'll do that. Anyway, so that's about it. So we quit there. So Friday, there's a paper already up there. So yeah, new homework, and anyway, I'll go through that on Friday. So all right.
Thank you.
All right. Thanks. Oh. Let's see what the data is like. What is going on?